Hello, my name is Jeff. So I just found this out about using this website I use for presentations, where if you want, these slides will appear on your laptop live and they will scroll as I scroll. So if you want that, you can go to this link, which you can't really see there, but I can read it. It's slides.com/jestrada/GDB Workshop with the dash. Yes? It's workshop, okay. And then /live. Could leave that up for a bit. I don't know. Is someone on it already and can tell me if it works? Works? Cool. Alright, so I'll start this. Alright, so this is a little dark and I was playing around with this earlier and I really like the color scheme I had for this, so I realized that the lighting works best when all the lights are off and I leave the whiteboard lights on. So I'm gonna do that because a lot of my screen is dark, so doing this would work out better. Is this fine for people? Like, you're not gonna fall asleep, right? Woo. Okay, so first thing, so for this workshop, I was planning on having it be somewhat interactive so that you guys can be working with GDB while I'm presenting. So if you want any of the materials that I'll be using while I'm up here, if you go to my GitHub, github.com/jestrada-ramos, you'll see the GDB tutorial is pinned on my profile, so you can download it if you want. And I'm not actually starting until probably 3 minutes down, so you have time to go through it and try to download the materials if you're interested. Again, if you wanna, you just go to my profile, just search up J Estrada Ramos, and you should be able to find it. Right. So if you guys are downloading that, while you guys do that, I'll talk about why you guys should learn GDB. So main reason for using GDB is it's great for locating bugs. It's a debugger, so it does pretty good at what it's meant to do. If you're wondering what it stands for GNU Debugger. Fun fact. And it's using a debugger like GDB is an awesome alternative to using something like a bunch of print statements in your code. I know before I would have about 30 print statements within a function just trying to figure out where my code went wrong. With GDB, you can actually step through your code one line at a time, whether that be assembly level instruction or code instruction. And then you can actually print out what the values of anything within your code that's happening at that moment. So it makes it easy to realize when your code goes wrong. You can also set breakpoints and watch points. I feel like breakpoints is straightforward that most people know. Watch points is not something most people use, I think. It just checks whether a variable is changing at each point, which I'll show you how you can do that. Another reason using GDB is a good idea is it's on a lot of Linux machines. If you get onto any Linux machine, GDB is likely installed on it. And yeah, and then if you program in C or C++, GDB is pretty good for that. It's its main debugger. And if you're taking 2011, GDB is kind of like what you need in order to pass Bomb Lab or using any other debugging tools. And it's free, unlike another debugger called IDA, which costs thousands of dollars. So GDB is pretty cool, and you're a cool kid. So yeah, James.
Could you go back a slide? I just need to.
Yep. Also, if you're wondering, that is what GDB can look like. If you're in the CS 2011 class, you've probably already seen this, but I'll be going over how you can get to that view and use it, as well as certain plugins. You good, James?
Yeah.
Alright. Does anyone else need this? Good? Alright. So things that I'll be going here is I'll teach you how to set up your code so that you can debug. There's only one thing you really have to do, and it's when you actually compile the code, which a lot of people forget. there's people within the operating systems course who are trying to use GDB, and they're like, it doesn't work, and I'm like, you forgot to do that, and they're like, ah. So it's a really simple thing. It's the next slide, so I'll wait for that. I'll teach you some useful commands for general debugging a C program. As well, I'll be using the debugger to do some general debugging on some simple programs. As well, I'll be using it to reverse engineer a couple of programs. And those programs include miniature bomb that I'm created, similar to Bomb Lab, as well as the Bomb Lab that they use for RPI instead of the Carnegie Mellon one, which is the one that we use in the 2011 class. So, any questions on this so far? All right. So I'm assuming a couple things from you guys because I can't teach everything. So I'm assuming you've already coded in C or C++ at some point. I'm also assuming you can use a makefile, as in you know how to type the word make in the command line. You have a Linux or a Unix environment that you can work on, because if you don't, I think you can get GDB on Windows, but I don't know how that works. And I'm assuming you know how to use the terminal, and also you know some assembly instructions for the second half of this tutorial. And I really hope you do if you are taking the 2011 class, because if you don't, then you might be a little behind. So, yes. So first thing first, you can't just use GDB on any program. It has to be a program that has been set up beforehand so that GDB can use it. So what you need for your code is, so usually when you compile your code, you type something like up here, gcc-wall doodle-that.c.o/ or -o doodlebug, and that'll compile your program normally, assuming that you don't have any errors in it. But if you want to use GDB, your program needs to have the -g flag in order to create a symbols table, so that GDB, once it reads in your program, it actually is able to tell what is going on in your program. Because if not, once you open it, it'll be like there's nothing here. Unless you're willing to go through all the binary in your code, GDB won't help you unless you have this flag. All right. And then this is also assuming that your code is able to compile. If it doesn't, then there's another problem. And so now we're going to get to the part where we're going to start using GDB, because I feel like personally I don't learn really well just from listening and watching. I learn by doing. So that is why I made the code available beforehand, and by beforehand I mean when you guys got here. And yeah, so the first thing that we're going to go through is we're going to go through this program. I called it simple step because it's simple and we're going to step through it. Can anyone tell me if there's anything wrong with this code? Just from looking at it. All right, you guys can stop looking. Oh, what?
Is it after all the print statements, it uses size as input, and the sharp pointer is just a...
No, there's actually nothing wrong with this. Yeah, no, there's nothing wrong with this code. The main reason I have it is so that I can show you guys some basic GDB commands without having to worry about, oh, there's something broken, I'm looking for something. Maybe I could have made the string smaller, but making it bigger doesn't actually affect the way this code works. It'll print hello world, goodbye world, or none of the above without any issues. So some of the commands I'm going to be going over just to show with that code is I'll be showing you how to use break, how to use run, how to use layout next, how to use next, continue, and print. And no, I'll do that now. So if you guys have the program already, is that too small or is it just at the top? All right, I'll make that bigger. Is that good? All right. So if you downloaded the repo that I had, all you have to do here is type make in the program, or you can just type make and it'll make all 3 programs that I have here for you guys. But just because I don't want everything coming up at once, I'm going to just do simple step. Alright, so now I have this executable called simple step, and we're going to use GDB for it. So to run it, you run GDB. I have to run the -n command just so that my plugins don't show, because I want to show you guys first how this looks like without any plugins, and then the name of the program. And then you get all this junk in the beginning, which I don't know anyone that's actually read all of that, but I just see a copyright sign somewhere, and that's good enough for me. So the first command that we're going to go over is the break command. So what break does, if you don't know, is it stops the program by the time that you reach wherever you set that break command. And the way you can use it is you can have it break on a function name, on a line number, or on a conditional. So in this case, after already seeing this program, a function that we can break on, which is usually pretty good for any program, is breaking on main. So before you start anything, if you break on main, you're at the start of your program. So for that, you can type the word break, or if you want the shortcut, you can just type B, and you get main, and it sets a breakpoint there. And then to run your program, you can type out run, or just type R, and it'll run the program for you. And then here, because main is the first thing that we are working with, it stops at the main. And I personally don't like this view of GDB because it doesn't really tell you much. So what I like to do is type out layout N, and what that'll do is it'll give you a new, they call it a TUI, text user interface, and then you're able to see your code and where you are in your code as you go through the program. So what was I going to go over? So we went over break, run, layout. So now we're going to do next. So far we're on the first line. If you want that line to execute, you just type out next, you press enter, and now you're on the second line. And then a shortcut for that is you can just type N, and then if you type N, it'll do the next one. So at this point, since it's a print statement, it should print out something. GDB is not really good at doing print statements, so it'll cut some things out sometimes. So in this case, it should have printed welcome to the GDB tutorial, but instead it gave me E to the GDB tutorial. But for the sake of debugging, that's not that important, because usually print statements aren't what you're looking for in your program. They're usually just to show things to the people. If anything, you would want to see what data is being printed and see how that got messed up. So then again, so whenever the text gets messed up, you can also type in REF, which stands for refresh, and it'll clean it up for you. And that'll be, later on, this layout can get really messy later, so it's a really useful command. And then you type N again, and you can just keep, after you press the command, you can just keep pressing enter, and it'll do the previous command over and over again until you enter a new command. So here I can just keep pressing next. And so now, here we're going to get into fgets. So this is going to ask users for a input. So after I press enter, I don't get the little GDB prompt anymore. So now this is standard in, so I can type in anything here. So the options I had were 1, 2, or 3. So if I type in 1, it goes here. And then I can just go to next again, and it'll go there, it'll print, it'll break, and then it'll be the end of the program. And now we exited successfully, and there's no source code available because we are now done. So what else is there? Okay, there's continue and print. So I'm gonna run this program again just so that I can show how those two commands work. So you can just type R again, it'll start it from the beginning, yes. So right now, the way you can use breaks is you can set them at a line, and let's say I wanted to break at line 12. I'll break there, and then GDB puts a little place marker here so that you know where your breakpoint is. So if I wanted to go all the way through this code and not have to press N over and over and over again, I could just press the seek option, which stands for continue, and that'll just go all the way into the code until it reaches a breakpoint or your program ends. So if I press continue, this is where the screen gets all weird. So if you just type in ref, puts it back to normal, and now we're on line 12. Any questions so far? All right, so then now we type in next, refresh, we can get an input, and then if I type something in, so like 2 this time, put it in. Now we can use the print statement, and here print usually works as in any other print in any language. It prints out variables. So at this point, if I just type in print input, it'll give me that I typed in 2. So that's useful later on when you want to see what values your variables have. And then, okay, I think that's it I have for this program. So if I just type continue, it'll just go all the way through. Goodbye world comes up here, the screen gets all messed up. I can type refresh, and now it's all better. And then you can quit by pressing Q, and you're back on your terminal. So those are some basic commands that are pretty useful if you're trying to debug regular C programs. So some other things that are pretty useful is the print command. You can print out your variables in whatever format you want. So if you print it normally, I think GDB assumes they're strings or tries to figure out what type they are. But if you want to print in a specific way, you can do it by using any of these formatters. So if you type in print/A, it'll print whatever you pass in as a pointer. So you probably get hex values afterwards. If you type in C, it'll print whatever value it is as a number. And then further on, it'll do what these other things are. And if you are in CS 2011, this is pretty useful because sometimes when you try to print or use the X command on variables or memory, you get some value, but it means nothing to you because we don't read in hex on a normal basis. So these are some useful formatters for your prints. Any questions on these? Alright, cool. So here's our second example. Here's some bad code. I don't think you can really tell what's wrong with this just from this. There are other functions in play. You can't really tell what those functions do because I wrote them, so they're not like legit. So can someone, I know it's pretty straightforward, but tell me what they think this program should do? Please? Julian? No? Alright. Well, this is supposed to be a queue. The first part is just an arbitrary for loop, which I was going to use to show you guys how to use watch points. So it literally means nothing. Everything after that, there's a queue, and I'm trying to add things to the queue. I'm trying to add the numbers of pi to the queue, take the numbers out of the queue, and after I add them and after I get rid of all the numbers I want in the queue, I want to print them, and that's about it. So if you go into the terminal and you type make bad code, you'll get a program called maybe segfault. So if you run that, it does weird stuff every time. So currently it prints out the 9 numbers, it adds numbers to the queue, it tells me the numbers that are in the queue are 3, 1, 4, 2, 6. That is only 5 numbers, and I tried adding 8. So something went wrong. And then I tried dequeuing 1, 2, 3, 4, 5 numbers, and they're empty. So that worked out fine. Then if I run it again and again, it segfaults sometimes. It only added 3 to the queue, so it segfaulted then. I only added 3 and 1. I'm looking for a specific edge case. And then sometimes it does this. That's pretty fun. Yeah, it just likes going forever.
Wait, is it gonna like crash your computers?
I hope not.
Let's find out.
So obviously there's something wrong with this code. And let's pretend we're not regular programmers and we decide not to look at our source code and we just go straight to GDB. Because I would recommend try to look at your source code first and then use GDB. So GDB-n, maybe segfault. You can break on main. And then we can go into our new layout. There is no source. That's because I didn't run yet. So if I run, there we go. So some things that I want to go through here is I want to show how to step into a function, how to use a watch point, and some of the info. Actually, I'll use info for the next code. That's a better place for it. But if you don't know what stepping is, this diagram over here kind of goes over it. So when you're trying to use a debugger, you can either step through code or step over code. So when you use the end command or the next command, you're simply stepping over any functions that you go through. But if you use the step command, you're going to step into it. So you'll be like this stick figure dude over here. So if you run step, you'll come down here, and then you can go through this code and see what's happening here. And once it's done, you come back up. But if you just type next, you'd be like, I don't care what happens here. I'm going to just go here and just take the output. Hopefully everything's fine. If not, I'll come back to it later. This makes sense to people? All right. So info, that's next, but back here. So we're here. We can just step through our code. There's a random number seed being set here. You'll see why that's relevant later. Right now we have a variable called x and it's set to 0. However, if we set a watch point to x, did I type that wrong? Alright, so I set a watch point on x. So what watch points do is it keeps track of that variable throughout your entire program, and if it ever changes, it'll let you know. So within this for loop, we're just changing x the whole time. So every time we go through the for loop, it's going to tell us. So if I just type continue, it stops and it tells me the old value of x was 0 and now it's 1. Then if you just continue again, it'll stop again, and it didn't. Why did it not? Or ref, what happened? Okay, next. Okay. All right, there we go. So it stopped again. It told me it went from 1 to 2. And then if I just keep going through this, and then again it stops and it tells me it went from 2 to 3. So each time you go through this for loop, it's going to tell you this is pretty bad. Well, it's only telling you it's bad because you said so. So if you want to get rid of a watch point or a breakpoint, you can just type clear and then what's it called? Info break. You can type clear 2 because, okay, so info break tells you what all your breakpoints and watch points are, and they all have a number. And then you can use clear to clear specific watch points. If you type clear 2, no breakpoint at 2. How do I do that? Okay. Well, if you type just clear, Jacob, do you know the command for clearing a breakpoint?
Have you tried unbreak?
Unbreak?
You can also try clear and then line up.
Clear 25. Alright, well, I'll just keep going through this until it's over. Okay, so now we're here. So now we reach the function, and if I want to step into the function, you type S, you go in, and now we see some code. And here is where you could probably find out why our code goes wrong. So can anyone tell me why this code is bad? Jacob.
It has like a 50% chance of just not allocating the next node.
Yeah. So if you ever write this, I am disappointed in you, because that'd be something really dumb to do, to only allocate memory sometimes. So here, each time you try to add a new node, sometimes it'll add it and sometimes it won't, because if you don't call malloc, it won't put it on the heap, and if you don't put it on the heap, it's non-existent. And that's why sometimes when we ran the program, you would have all the elements in there. Sometimes you'd have a couple, and then sometimes it would do that weird thing where it would just print the last element over and over again. So yeah, so here we basically found the problem with our code, and just off the first one, it skips allocating memory on the 3. So that's off to a bad start. And then does everything else. It messes up the screen. And yeah, so that's essentially what the step function is used for, just to go into functions and see what's happening in them. I can set a breakpoint at 39, and we can continue till then. And before you even get to there, you segfault, and that's probably because we don't have any memory allocated for some of the nodes, and so when you try to access them, it doesn't quite work out. So any questions on this? Because that's probably about it for going through regular C programs. And the third example is going through a little tiny bomb that I made. So usually when you deal with these kinds of programs, you don't have any source code available to you. I know in the 2011 class they gave you that one C file, but that C file didn't really tell you much. It was kind of like the Q one that I had up here, where it just had a bunch of function calls, but just the function calls didn't really tell you anything about your code. So here we're just going to go through a smaller bomb. And some things to think about while you're using GDB for these bombs is that you're not quite looking for a bug for these kinds of things. You're more trying to figure out what the program does. You want to decipher it, not fix it. Breakpoints are your friends in this one, especially because your grades are dependent on them. If you blow up your bomb in 2011, you lose points, so that's not good. Using a nice layout is really useful to visualize what's happening in your code. This is why having some plugins are good. I know during lab today, I think each section talked about a different plugin. Some sections talked about one called Jeff, some use one called PETA, other ones use GDB dashboard, and I think someone mentioned radar, but then they said don't do that unless you're ready to learn something brand new. And using the info function is also useful because it lets you know information about the program at any given point. And yeah, so some differences between trying to go through assembly and regular C code is to go through the next command in assembly, use NI instead of N. If you run N within assembly, it'll probably go through a couple instructions, because usually for each line of code there's a couple of instructions that take place. Using SI is to step into a function, but at the assembly level. So it's kind of similar to the step function in regular C programming, but it's more focused towards stepping into a call to a function in assembly. Break, you can set breakpoints at memory locations now. You can also set them at function names plus the offset. And then you can also print registers and variables, which is something you usually don't do when you have just C code. And then using // and then any of the options that / has lets you print memory locations in a variety of ways. Again, this is also the same what's it called, options for print. So if you wanted a pointer, you'd use P. If you wanted an int, you'd use D. If you wanted a character, you'd use C, and more other things like that. And so yeah, so for X and FU, you can go through the help command and figure out what each of the things do, but essentially X is the name of the command. N stands for how many units of memory you want to print, and you can specify what kind of units. So if you wanted to print out 500 bytes at a given location, you can type X/500, and if you type the letter B, it'll give you bytes. So it'll give you the 500 bytes from that location on. And because you probably won't be able to fit 500 bytes on your screen, it'll probably give you pages of them. So you just have to click enter to go through. F is for the format, which is the same one as strings, where you can have, again, P for pointers, C for characters, D for integers, and other things like that. And again, units, you can print, look at memory in chunks of size of your choosing. So you can go by the byte, you can go by half a word, by a word, or a giant word. Any questions on this? Yes?
What is a word?
A word in this case, if I remember correctly, is 4 bytes, which would be the size of an integer. So if you wanted to print out a bunch of integers, you can do X/some number WD, and it'll print out that many integers for you. Any other questions? Okay. So now we're going to go with an example with Lil Bomb. So I have 2 phases on this bomb. The first one is a string comparison. If you went to the 2011 lab today, it'll be phase 1 of your bomb. That will be pretty straightforward, but then the second phase is a buffer overflow. You guys having gone over that in class, this is more relevant to what your next lab will be, because one of the phases for that lab would be very similar to that problem. So, yes. So, quit out of this. Clear my screen. Let's do make clean. So, if you type make little bomb, or if you already had all of them, I typed that wrong. It gives me an error saying there's a function that's not safe, which is a function you guys will be exploiting within Attack Lab. But yeah, we're gonna go over it. So let's just run GDB with the bomb, because you guys already know kind of what it looks like. Did I not make? Oh, it's just called bomb. GDB bomb. So first we'd like to set breakpoint at main. Something that I like to do at the beginning of every sort of binary that you try to exploit is try to run info functions, which gives you a list of all the functions that GDB has available about the program. So in this case, these are all the functions that GDB knows that exist. So some of these are familiar, like printf, string compare, gets, malloc. But then you can also find out these other kinds of programs called main, phase 1, phase 2, and explode. So if you were to run this at the beginning of your bomb in Bomb Lab, you would see phase 1, phase 2, phase 3, and then some other phases that if you don't know, you should know, and potentially could give you extra credit. So you should look into that. And then there's the explode function, which pretty much self-explanatory. If you hit it, you explode. Any questions on this? Cool. So, did I set one at main? I did. So I can just run the program, go into my nice view, and because of how they set up the bombs, you don't get to see the source code really, but you can see the assembly, and along with that you can also see the registers and the assembly at the same time if you'd like to within GDB. And here it looks like there's not much space for it, but that's because I have my text zoomed out so that you guys can see it. But once you guys have like a regular font on your screen, there's more room and everything fits nice there. And yeah. So start off, we know there's phase 1, so we could set a break at phase 1, and then we can continue up until that point till we reach. So now we can just step through the functions. Well, we can go through and disassemble it first so that we can see the whole thing. So I'm gonna do this as phase 1. And let's make this smaller. So here, the first couple lines are things that happen at the beginning of any function. It's just setting up the stack. It moves the base pointer to wherever the stack pointer is, and then afterwards it subtracts from the stack pointer. Right? Can't see from here. Yeah, subtract 16 bytes. So that means we have 16 bytes within our stack that we're playing around with, which hopefully they covered in your lab sessions. And then we do some fun stuff. We're calling some functions, call Q, call Q, call Q, and they're all calling the same thing. However, all these just are print statements essentially. So as you go through them, let's go here. So as you go through them, once we call Q, it says, I see that you've come to defuse this bomb. Wahaha. And then you keep going, and then it has another one. You'll never know how to defuse this bomb! Exclamation point. And then keep going. You'll be a fool if you thought you could simply defuse it. I was having too much fun with this. And now we're doing load effective address. So it's at throwing something in from memory into RAX. So once you go in, you can now type $\, $rax. Dollar signs are usually used to reference registers. So if you do that, you get some weird numbers, but that doesn't really mean much to us. So what we can do is do $x/s and get rax, and then we get this nice string here. Roses are red, violets are blue. ACM is the best, and so are you. Woo! All right, I didn't get much from that one. Okay. All right, so now we're moving things around. We're moving RAX 8 down from the base pointer, so that's essentially throwing it on the stack. And then now we're moving 8 into the EDI register. And then we're calling the malloc function. So we're just gonna allocate some memory within the heap. And then again, we're moving things around. And then I'm not really explaining these much because you guys probably already got the gist of this within lab. Unless someone doesn't quite understand what's happening and would like an explanation. Yeah?
I didn't quite, like, I just, if I can get a refresher then.
Okay. So, can I scroll here? Okay. So
It's just a bunch of moves.
yeah, we're just moving a bunch of data around. The beginning up here is call Q, just calling functions, and in this case, puts is essentially our print statements, which is what put them on there. And then here, this is pretty much the biggest part of this program. We got something from memory and threw in our register, and it was a pretty English-like sentence. So that's pretty much like a key to like, okay, this is important.
Right. Oh, okay, gotcha. I was just wondering what all of those move commands down there were necessarily doing.
So most of these is just setting up so that it can call this function. So if I remember correctly, it'd be putting 8 into EDI, which would be a parameter for malloc.
Are you going to show you the assembly at the top?
You type out layout N, and you can just click that over and over again, and it'll give you different views. So if you want just the assembly, you can get here. If you want the just the registers, you could get here. And if you want both, you get here. And I just typed out layout n and then just enter a bunch of times until you get what you want. Okay. Any other questions so far? Okay. So then we keep going. Now it's asking us for our input because we're at the gets point. So what should I type in here? What do you think, Julian?
I think you should try to type in the string.
Which one?
The one that is loaded from memory.
Could you say it for me?
I can't seem to recall.
Okay, hold up. I'll scroll up for you. Wait, I can't scroll up here. Damn it. Okay. Alright, I'll just type it.
Sorry, recently became illiterate.
Huh?
I think you're supposed to put roses are red.
Did I not type that? Oh, I said rose. Okay. Roses are red. Violets are blue. ACM is the best. So are you. What?
There might be a comma and
This is the best. Oh god. Alright, let's see if this works live. Now we'll see how to use GDB, right? Alright, so after doing that, because we call the function, it changes a lot of things. So that's why all of this is white. So these are all the registers that got changed while doing this. And there was an extra white line here for no reason, but these are all the registers that were used. All these other ones were also changed. I'm assuming you guys probably have all your registers showing at once. Here, just because I'm zoomed in, I have to scroll through them. But yeah. Also, if you want to scroll through different windows in this view, you can just type focus N, and then you'll get through different windows. So right now it says I'm on the command line. And then if I type again, now I'm in the assembly window. If I go again, I go back to registers, and go again, I'm back here. And that command doesn't exist. So now, here, we're moving something from that is 16 bytes away from the base pointer to RDX. So if we go through it, and then look what's in RDX after, we see we have this input. And then next, we're moving something that's 8 bytes away from the base pointer with an RAX. And if we type that in, we'll get RAX. And are these the same? Okay. And so are, alright. So they're the same. Cool. But now we're also moving both of these things into RSI and RDI. And then I don't know if they went through it in class, but RSI and RDI, those are the two registers that are used for parameters for functions. So I think RDI is the first one and RSI is the second one. So there's also other functions, which I don't remember the order of those, but in your book, it'll give you a list of saying RDI is the first, RSI is the second, and it'll tell you like R8 is the third, R9 is the fourth, or something along those lines. So when you're working with functions, if you see that a bunch of things are being moved into specific registers before calling a function, that's a pretty good sign that those are parameters for that function being called. Any questions on that?
Hey Jeff, what if my function has more than that number of registers as parameters?
If it has more registers than parameters, then they all just get pushed onto the stack. And then if you were to do the x/n or whatever on the beginning of the stack within that function, you would see all those extra parameters. Any other questions? Okay, cool. So now here, we call a function called string compare, which is just the regular string compare function with C. Does anyone know how this one works or would like to explain it? Because it would help in trying to figure out what this next line will do. Okay, so what string compare does is it takes two strings, it compares them, and then it checks how different one string is to the other. So if both strings are exactly the same, the difference between the two strings will be 0. If the first string is bigger than the second one, it'll give a positive number or a negative number. I forget which one, but essentially it'll give the how different they are in terms of characters. So in this case, because both of our strings were the same, when you run it, all outputs of a function usually go into the RAX register. So over here we see that RAX has turned into 0, and that tells us that both of these strings are equal because there's nothing different from one versus the other. So then what test does is it takes whatever values it has, it ANDs them, and then it sets any flags that come out of the AND. So in this, yes?
Is RAX mainly used for output? For functions?
Yes.
Okay.
So here we're testing the output of our function from string compare, and so you just AND the EAX with itself. If it's 0, you'll get 0, and if you have any other values, you'll get that value again. And then here you'll be able to see, I have to go here. Here you can see that the Z flag was set after running that command. So because it was set, the jump not equal, oh, that takes it away, will, hold on, where am I? Oh, okay. $123. So the jump not equal, because they were equal, but the 0 flag was set, it's not gonna jump, right?
So EAX and EX ANDing together
Gives you 0.
will give you 0 if they were equal.
Yeah.
So that jump will only get called if they weren't.
Yeah. Okay. It's some backward stuff going on. But yeah, so it doesn't jump because they were equal. And then now we're moving something into RDI, and instead of trying to type out 0230 RRP, I'll just run it, and then you can just call whatever's at RDI. And then, oh, look at that. You've diffused this phase, the evil plot is ruined. And then after that you just, oh, that's gross. You go to this jump statement, which is going to jump no matter what. And then it goes there. And then you just make it all the way to the end. And you've defused phase 1 of the tiny bomb. So now phase 2 is mostly about buffer overflow. And to quickly explain what that is, essentially, is usually when you have variables declared within a function, they get put in the stack. And so, like, for example, if you put an integer into the function, and then afterwards you declare an array of, let's say, size 4, within the stack, those 4 elements of the array and the integer you set up will be all next to each other, and they would take about 8 bytes. And then the way buffer overflow works is the get function within C has a vulnerability in which it takes input from the user, but it doesn't ask for how much input. So what you can do is, usually if you use get to fill in the array of 4, but you actually fill in 5 things, you would actually be overwriting things within the integer, because let's see, how can I show this? I don't want to quit. So if this was our stack, and we had an integer here, which takes up 4 bytes, and then we had an array of characters, which were also 4. When you use get, it would try to fill these 4 things in with whatever you type in, but if you type 5 things, it'll overwrite this last piece of your integer, affecting basically overwriting whatever you have on there, which could later lead into problems that happen later on in your code. Does this super simplification make sense to people? You'll probably go through this eventually with Suraldi, and maybe he can explain it better. But yeah, so the next phase of this bomb is essentially trying to work with that. So if we break at phase 2 and then just continue, I don't want registers. So if you look at this code here, you can see that I don't want to go through all the assembly, so I'll probably just simplify this to saying that memory is allocated within the stack, and there was an array that was set in, and also an integer like how I described earlier. And over here, where is it? Where is that comparison? So over here, at some point earlier on here, we set up a part of the memory to be equal to 0, and that's why here it's asking to compare, and at some point it's asking to compare 0 with some point in memory here. And this point in memory here is 4 bytes from the base pointer, and 4 bytes is the size of an integer. So it's taking those 4 bytes and comparing it to 0. And if it passes, then it'll blow up, and if it doesn't, it won't. But because it's set at 0 in the beginning, most people will go, why is this 0? How do I change it? There's no way in which what I type in directly changes 0. So when you call this get function up here, it takes in what you have there in memory, which in this case I had 4 bytes, and then if you type in 5, that extra byte would overwrite what is in that one integer. And then the way if statements work is if it's equal to any value, it'll set it to true, and then it'll do the thing. So just changing one of those bytes is enough to create a change within this function. Does that make sense to people? Okay, because we're running out of time, I want to show mostly the plugins that you can get for GDB, which help a lot with this. So a lot of people have used PETA, Jeff, and GDB dashboard. I personally use Jeff mostly because it sounds the closest thing to my name and it looks nice. So this is what Jeff looks like. I already installed it, and so you don't have to do anything special for it. You just run it normally, and then when you start, everything looks normal except the prompt, instead of saying GDB, says Jeff. And if you just set a breakpoint at main and then you just run it, you get all of this nice information here. You can't see it all at once because I'm zoomed in, so I'm gonna zoom out. So yeah, so essentially here you get all of the registers, and you can see all their values, and if it can, it'll try to convert whatever is at those registers into strings or to whatever value it makes most sense to represent to you. And so for example here, there's a point in the stack where it has the directory where the bomb is, and it converted it into a string, and it has it written out there for you. And then here it also has the assembly code for you, so you can go through it, and then if you set any breakpoints, it'll tell you once you stop there and why it stopped there, instead of just arbitrarily stopping. And yeah, so if I set a break at phase 1, and I just go to there, and let's see, where do I want to set a breakpoint? or just step through it. It'll show you, once you get to a function, it'll actually show you a preview of what that function does before you, so you can make the decision whether or not you want to step in or just jump over it. But because we know put is essentially our print statement, it's not that important, so we can just step over it. And then we're moving all the things around, and a bunch of those again. And where is it? Malloking. Then we get to get. After we run it, it gives us the prompt. We can just put. I should have made this shorter. And so here, this is one of the things where it's really useful, is it'll show you these kinds of things on the stack. So we typed in this phrase and it threw it on the stack, and now we can actually see it instead of looking at hex values, which most people can't read. And then if you keep going, it'll keep moving things around, and it's going to compare things, test. And then also it gives you things like this. So once you get to a jump and you're trying to think, oh, is this going to go or not? It'll just tell you if it will. So here it tells it's not going to jump because the flag wasn't set, or it was set because that's a double bang. So yeah, it keeps doing things like this.
How would you know otherwise if it will make the jump if you're just using regular GDB?
So if you're using regular GDB, depending on the jump, yeah, so if you have a regular jump, it'll jump no matter what. If you have a jump not equal, it'll jump if the 0 flag is set. Yeah. So here, to see the 0 flags there's register called the EF flags, which is just one register overall, but that register is split up into little pieces so that each part of that register represents a different thing. So there's a 0 flag, there's a carry flag, there's a parity flag, there's all these other flags, which if you read your textbook, you'll find out what they mean and how they're useful. And yes. Any questions on plugins? All right, that's pretty much all I got for you today. If you want to mess around with my code, go ahead. If you like the bomb lab and want to do another one that's like it, that's by another school, there's an RPI bomb in there that you can play with. It's actually a lot prettier than ours, I think, because if you run it, it looks like this. When they connect it to the server, it has a timer, and they actually give a hard time limit on their students to defuse the bomb. So yeah, and then these are like the cables within, like, cut the wire. So once you solve a phase, like, this will disappear here. And yeah, so if you want to mess around with that, go ahead. And thank you for coming. Woo!